Thanks a lot for organizing all this. This is a journal club, and for giving me the possibility to talk as well. I turn off my video, I guess. Okay. Okay, so I will be talking about hard X-ray, photon-in, and photon-out spectroscopy. I thought in my presentation I put in together some slides about things that I find interesting and maybe useful to present in this talk. I'm a scientist at the ESRF. I do X-ray spectroscopy for a living, and so this is what I will be talking about. First, before I start, an advertisement, a little publicity for a program that is being developed at the ESRF for ligand field multiplet calculations. Many of you, know the code that is hosted by Frank de Groot at Utrecht University, the Theotole multiplet code, and this is let's say a continuation extension of this kind of calculation. It's based on the but I take the laser pointer. So it's based on a code for quantum mechanical calculations by Moritz Haferkort, a professor in Heidelberg in Germany. And the interface on top is programmed by Marius Retigan at the ESRF, and everything is written in Python. The code is written in C by Moritz for the calculations, and the interface on top by Marius. And it has a nice feature that calculations can be done in many different symmetries, local symmetries around the absorber atom. And it has included many different spectroscopies. So you can download it, the URL is given there. And everybody is invited to have a look. It's very educational. So for giving lectures, it's a very nice tool to explain crystal field theory and spectroscopy. And it's a very nice tool, and everybody is welcome to test it, give feedback to Marius, and hope maybe even contribute to the project, as it's open source and programmed in Python. Okay, I start here. So the first part, I talk about X-ray emission, the X-ray emission spectrometers that we have at ID26 at the ESRF, and I will then include also some general discussion there about emission spectroscopy. So I start here. First, you can group emission spectroscopy roughly in point-to-point scanning spectrometers or point-to-area dispersive instruments. So this is a rough distinction I make here. They are hybrid instruments that do a little bit of both. But this is, I think, just to explain it, it's probably the easiest way to start like this. So for either you have the so-called Rowland circle, and you have your source, analyzer, crystal, and detector on this Rowland circle. Then you may have in this geometry two possibilities. You have a Johansen cut crystal or a Johan cut crystal. In the Johansen crystal, you really achieve ideal focusing in the meridional plane. So you have the goal here is that all X-rays from the source, they hit the surface of the crystal under the same angle theta. In order to ensure this, you have to have a crystal that is cut in the so-called Johansen shape, that the crystal planes have a radius r, and the surface of the crystal has a radius r/2. So it's kind of something like an asymmetric cut, but the asymmetry angle changes depending on how you move away from the central position. If you have this, as I said, that really all X-rays emitted from the source hit the crystal surface under the same Bragg angle theta, and you have the ideal focusing on the Rowland circle here where you put the detector. Such crystals are difficult to make, and what usually people do, they do not have this asymmetry angle in the crystal, so the crystal planes are parallel to the surface, and the crystal has a bending radius of r. In this case, you have an error, delta theta here, which is the so-called Johan error, and the focus is also not ideal. Anyway, so these are the two possibilities, frequently used for a scanning instrument. Then alternatively, you have a dispersive instrument. I show here the von Hamers geometry, where the X-rays emitted from the sample hit the crystal surface under different Bragg angles, and you use a position-sensitive detector and get your spectrum there. Roughly, I hope most will agree with me that the advantages of this instrument are you have a flexible scan range, so you have to, in order to do a scan, you move the crystals and the detectors at the synchrotron radiation source, because the source volume here cannot be moved. So you have to move your parts mechanically in order to change the Bragg angle. That gives you a flexible scan range. The fact that you use the entire crystal surface at one energy within the energy broadening makes this instrument very efficient for high energy resolution fluorescence detected XANEs. I will talk about this a little bit more later. The disadvantage is that you have complex mechanics. I told you that the crystal and detector, they have to be moved around. You don't have to do this in the dispersive geometry, so the mechanics are much simpler. That is very nice. So if you have a complex sample environment, or if you want to mount an ad hoc instrument in your setup, it's very easy to do. You just need the cylindrical crystal and the detector. It's ideal for single shot spectra. That's why people use them at the free electron lasers. You may have problems if you have very dilute samples, because a large exposed detector area may give rise to a background in the spectra that is higher than in such an instrument where you can put a slit in front of your detector. And the scan range is less flexible, right? You can move them around, but your scan range is partly given by the dimensions of your crystals. Yeah, as I said, they are hybrid instruments where you use a Rowland geometry, but still use some kind of dispersion, or place your sample, your source inside the Rowland circle, and then it becomes dispersive. I don't want to go too much into detail. I'm showing this, why? Because at the ESRF on ID26 and many other beamlines, many users, or most users actually, they want to do this high energy resolution fluorescence detected XANEs. And that's why many instruments at the ESRF use this Rowland geometry, right? Because we want to use the entire surface, the available solid angle, in one energy, in order to have this HERF as efficient as possible. Yeah, some points that are maybe interesting. So now I show the Rowland circle here. So this would be the source, crystal, and detector. If you have a Bragg angle of 75 degrees, it looks like this. And if you now plot the Bragg angles on the crystal surface, you see that you have a dispersion on the crystal. So the X-rays that hit the center of the crystal have a different angle than outside. So this is the Johan error that is you can calculate here analytically. It is interesting if you now introduce a miscut, but a fixed miscut, not like a Johansen miscut, but a fixed miscut over the entire crystal surface. And you choose this miscut to be 15 degrees, you can actually eliminate the Johan error, because the X-rays hit the crystal surface at 90 degrees and hit the detector there. But what you see then, you see the Johan error, it disappears in the dispersive or meridional direction, but you get a broadening now out of the Rowland circle, so you get a broadening in this direction. And I realized during the ray tracing calculations, I realized that they're exactly pretty much the same. You see here pretty much the same magnitude. This arrow. So it was proposed. I show the reference later in a publication. It was proposed to remove the Johan error by choosing the miscut such that the X-rays hit the crystal at 90 degrees. I'm sorry, choose the miscut here. But I think using the ray tracing calculations, you do eliminate the Johan error, but you do not get the, you still get the same energy broadening. So you don't reduce your overall energy bandwidth. Another comment here, if you choose to displace your crystal out of the central position here, and you, without introducing a miscut into your crystal, you will degrade your energy resolution of the instrument. So whenever you decide to move your crystal out of the plane here, up there, you have to do this together with a miscut in the crystal. You have, this is the instrument now on ID26. that we use. So you see, we use 5 analyzer crystals in this Roland geometry. We have Johan crystals in a symmetric arrangement. The sample goes here, it's hit by the X-rays, and then the X-rays hit the analyzer crystals. What one challenge is, if you use the 5 crystals, not to degrade your resolution. So we, by adjusting the angles for each crystal or adjusting the height of each crystal, we move the elastic peaks on top of each other. And then you see here each crystal, the center of mass of each elastic peak for each crystal, they coincide there. However, you see that the crystals are not perfect, so each crystal has a slightly different broadening. So that, of course, the final energy resolution is a convolution between all the broadenings, but we try to move all the peaks, the elastic peaks, on top of each other. So each of the analyzer crystal, the energy calibration, relative energy calibration between the 5 analyzer crystals, coincides. We use at the moment we use a single element detector at the beamline, and that is due to the fact that we want to do continuous scans or fast scans. That means we need acquisition times per data point of, let's, in the millisecond range, so 10 milliseconds or even faster, 1 millisecond. At the time we built the spectrometer, there were no two-dimensional detectors available that would give us such fast frame rates. This is changing now, and detectors are becoming faster, and you could imagine putting a two-dimensional detector there. And there is also one idea that can be done. It's not a new idea, it's actually how a spectrometer on ID20 at the ESRF works. It's described in this publication there. You see here what you see on the detector. This is the focus from the 5 analyzer crystals on the detector for a Bragg angle of 80 degrees and for a Bragg angle of 75 degrees. You see, if you decrease the Bragg angle, it becomes larger, the focus becomes larger. And but what you also see, the colors here, they correspond to different energies. So this comes there in this case from the Johan error that I showed you before. If you now decide to move your detector out of the away from the Roland circle, you split up, you separate the 5 foci from the analyzer crystals. In D here, actually you go to the condition where you get you go from the meridional focusing to the sagittal focusing, and this is something in between here. And there, nicely, you could think about doing actually a dispersion correction, right? If you have a position-sensitive detector, you could assign the different areas on the detectors to different energies, and then move them or in the data processing process, in the data after the data acquisition, you can move the different peaks on top of each other and increase the energy resolution of your instrument. So that's one idea, one possibility one could do with a position-sensitive detector. So that's one of the things I would like to try at ID26 at some point. The next, we have a second instrument at the beamline that was recently commissioned. That was built. It's a large collaboration or huge effort by many people at the ESRF. In the beginning, it was spearheaded by Mauro Rovezzi, and then in the past 2 years, it was Blanca who managed the project. And I'll show you. Well, I should mention it was financed by this grant here, and the PR in this grant is Alain Mousseau. The tender X-ray range roughly starts at 1,500 by convention, 1,500 electron volts going up to 5,000 electron volts. And many of you know it's difficult to find crystal reflections in this energy range that are close to 90 degrees. Usually, in order to minimize your energy broadening, you want to work at Bragg angles above 75 degrees. Difficult to find crystal reflections, as I said. So we have to build a spectrometer that goes to lower angles. Also, we have to work with Johansen crystals in order to minimize the Johan error. So there, I give you some the curves here, the energies as a function of the Bragg angle for quartz, silicon 111 and silicon 220. Of course, then there are the higher order reflections as well. that I'm not showing here. But you see that we can cover the K-alpha lines of a few lower Z elements, phosphor, sulfur, chlorine, and then interesting, of course, the L-alpha lines of 4D transition metals, and then the actinides as well. So a very interesting energy range, as many and our host Jerry knows very well. Very interesting energy range, and for this energy range, we built our spectrometer, a tender X-ray spectrometer. We decided to use Johansen crystals to be able to work at small Bragg angles, and they're difficult to manufacture, so we decided to make them cylindrical. And we did ray tracing calculations in order to find out, to determine the energy broadening that we, or the size of the crystals that leads to an energy broadening that we can accept. And we finally came up with the dimensions 80 millimeters by 25 millimeters. So cylinders of 80 by 25 millimeters. And you see here again in this plot where the deviation of the Bragg angle across the surface is shown. That so this is the meridional direction, and you see, because they're Johansen crystals, we don't have the energy broadening in this direction, but we have a broadening. If you go out of the Rowland circle, you get this broadening in this direction that you can actually calculate quite easily. And well, using this formula and ray tracing calculations, we decided then we should not go broader than 25 millimeters in the sagittal directions. So this led us then to the size of the crystals. Then of course we want to have a large solid angle, as large as possible, and we decided then to have a total of 11 crystals mounted there. Now you see how on this slide how the crystals should move as a function of the Bragg angle. So this is 85 on the left here, and then 35 degrees of Bragg angle. And you see that the motion is complex for those 11 crystals. If you want to do this, you would need 4 degrees of freedom, like in the spectrometer that I showed you before. You would need 4 degrees of freedom for each crystal, 2 rotations and 2 translations, and then you have to move the detector as well. And that quickly becomes very complex and very expensive. And then there was, the people working on the project had this very nice idea of realizing this motion by having like, by using this so-called sagittal plate. So you have the 11 crystals mounted here, and they all sit on this sagittal plate, and the sagittal plate can rotate, or is rotated by a big rotation there. The rotation axis goes through the center to the surface of the central crystal here, and that gives you the correct the Bragg angle, at least for the center crystal. The crystals then left and right from the center crystal, they are moved by something we call the pantograph. That means you have 2 actuators here, left and right, and they pull on this nifty mechanical arrangement here. And if it's done correctly, then all the crystals here on the side move in the sagittal direction the way they should move in order to be precisely on the Rowland circle. And that actually works. An engineer can actually figure that out, how this is supposed to move. If you check on Wikipedia and see what a pantograph is, and then you get this nice image for a pantograph, and then you also understand why it's called the tender X-ray range. So we were very happy that we found this solution because you can realize the precise motion of all crystals using this pantograph in connection with the sagittal plate. Also the advantage is that you can actually minimize the errors, right? You want to have in the vertical direction a very small angular error, and if you really use a highly polished plate and this brass pantograph here is held on the plate by magnets, you do achieve actually a very precise motion that you would not be able to achieve by having 4 stages, rotation translation stages for each crystal. This is how the this is how the spectrometer looks. We decided to put everything in a big vacuum chamber. The X-rays come here. There's a sample tower. The sagittal plate with the pantograph is mounted here, and there the detector is mounted there. and all the stages here ensure the correct motion. Then you see here when the chamber is closed, it's a big and heavy thing mounted on some rails that you can move them around for maintenance and aligning it with respect to the beam. We have several ports there for cryostat, for inserting the sample, load logs. Yeah, so this is our new instrument by ID26, a tender X-ray spectrometer. It's windowless, basically from the source, so you can go very low in energy. The pressure inside the chamber is actually very good. It's lower than 10 to minus 5. Actually, we go to 10 to minus 6, so we can use a cryostat without any. So the vacuum is good enough to act as an insulating vacuum when you work with the cryostat. We have the liquid helium cryostat there, and we can use in situ cells. So we started doing some in situ experiments as well inside the chamber, and as I said, that all works. The detector was a big challenge. It has to be quiet at very low energies, and it has to have a very large area. I show here an image of the focus on the detector at well, in the worst case, 35 degrees Bragg angle, 0.5 meter bending radius. So you see it gets very large, more than 50 millimeters in the horizontal direction, and more than 40, almost 40 in the vertical direction. And we decided to build a gas proportional counter. It was built by the ESRF support groups. We have 16 wires there in order to get count rates to a few megahertz. It is quiet at very low energies. And as I said, has this large area. We put a gas inside, 15% carbon dioxide in argon. And it's actually, it's compatible with the vacuum. It has an inverse vacuum, so the whole electronics inside the detector are in air, and then there are hoses going out from the detector chamber outside, bringing all the cables outside the chamber, and of course inside all the hoses is air, and the electronics inside are cooled, and only the logical pulses they exit then through the hoses. You see here the signal of 2 keV X-rays on the detector compared to the dark spectrum. So it is indeed very quiet. What you see here, the spike is a cosmic, I think, cosmic event. And so we are happy that detector works and it's quiet at low energies and does what it has to do. And maybe I go back to this image there. The 16 wires give us some position resolution in the horizontal direction. And we can use this position resolution actually to do something like a dispersion correction, right? Because the energies of the X-rays here on the side are different than in the center because of the error that we introduced by using cylindrical crystals. And this can be compensated partly using those 16 wires. Just as an example, so this is the tin, a tin L3 edge measured in total fluorescence yield is the black line. And then you see the sharpening effect that we know from Hertz spectroscopy. And it's interesting, you can do this with a silicon 111 reflection at a very bad Bragg angle of 35 degrees. You already get the blue line here that is sharper than the black line. If you go to higher Bragg angles where you reduce then the broadening, you get the red line here where you nicely see then additional features coming up in your high resolution Zane scans. Well, another example, it also in tin, in some elements, you're interested actually in looking at the L1 edge, where you look at the SP transition as opposed to the PD transition at the L2, L3 edge. For tin, this is interesting because the 4D shell is filled. And if you want to study your oxidation states, it's nice to look at the P density of states. And this, by using an emission spectrometer, usually if you do this in transmission, you have the L1 edge sitting there on this high background from the L2, L3 edges, and using the emission spectrometer, as many of you know, is you get rid of this and you get nice L1 spectra for tin. So this is just a nice example that I wanted to show as a proposal of what can be done in this tender X-ray range using a spectrometer like this. There I stop. Are there questions?
Yes, there are a few. I guess first, what roughly is the spatial resolution for that wire detector in each direction?
Oh yeah, now I should have looked up the numbers. It's a few millimeters.
Okay.
You can see there are 16. Actually, the outermost wires, we are limited. I didn't say this. We're limited by the available sizes for the window there. There's a MOXTEC window with a grid, so a very thin polymer on a grid, and the size there is limited. Yeah, anyway, it's a few millimeters, I think maybe 4 millimeters between the wires. But
okay.
It's in the publication. I give the reference for the publication there.
Got it. I liked your discussion of that parameter alpha. Did you consider whether there could still be a benefit to having a non-zero alpha if you wanted to get rid of the bending broadening because of penetration of the beam into the analyzer material?
So
it's a high energy problem.
Well, I don't know. We have to discuss or doing ray tracing. So it's actually there's a So my colleagues on ID20, there was Marco Moretti, and they proposed this in this publication there with this, and then you can contact them. They know better, and tried this. And I was curious, using the ray tracing, what would happen. And I just put this out there as a discussion. I may do something wrong, but from the ray tracing, you do not gain anything in the. I would not say that you gain. You don't. It's very interesting. You don't gain anything in the resolution. I was surprised myself. So as I said, I just wanted to show it here for discussion. Maybe I made a mistake, but at the moment I do not see any gain.
I see. Okay. What's the Rowland circle diameter for the tender X-ray spectrometer?
We can work at 0.5 meter or 1 meter.
Okay, good. Paula, you have a question?
Oh, yes, it's more practical. Hi, Peter. Thank you very much.
Hello.
Very interesting instrument. So basically, for the using catalysis, the cell that you were mentioning, can it handle gases and temperature?
We are working on. We are currently developing cells, right? So yes, I don't think there's much. We're not very limited, right? You can do all kinds of gases. You can heat up. You just have to build the cell, right, and adapt it to the vacuum conditions and to the low energy, right? You have to think about the windows. We need a rather large window in order to so all crystals see the samples. But anything can be done. Well, most things, not anything, but most things can be done. We have to discuss with the sample environment, and it can be done. Yeah.
Okay, thank you. I will contact you privately later.
All right. Seeing no other questions, you should continue, Peter.
So now I just want to say a little bit about okay, Photon-in, Photon-out spectroscopy. I'm not sure if the community wants to decide on an acronym for this. I'm not sure. So Photon, just quickly, as most of you know this, so usually you do fluorescence detected absorption spectroscopy with a solid state detector. We have a resolution of maybe 115 electron volts for iron or manganese K alpha. And then we use our spectrometer with the analyzer crystal. You get the higher resolution. You see the chemical sensitivity in your emission lines. And so we like, for the nomenclature, we like to use a partial fluorescence yield for kind of standard fluorescence detected absorption spectroscopy, and we use high energy resolution fluorescence detected absorption spectroscopy when you use a crystal analyzer. To be historically correct, there was first done this high resolution scans by K.O. Hemmerlein in '91 on dysprosium. This was a PRL, and you see this nice the 2p4f excitations that suddenly appear in this kind of scan. They were sitting on the alpha line of dysprosium, and then Paulo Gara in '95 pointed out to you that this is not really an absorption spectrum, but that you get actually you have to be careful. It's a two-dimensional thing that happens there. You have to plot your spectrum, the incoming energy versus the energy transfer, and you get very lot of structure and features that do not necessarily correspond to an absorption spectrum. So what happens there? So I plot this here in a total energy diagram: ground state, excited states, you have discrete excited states or a continuum excited state, and then you decay into the final state. There's a lifetime associated with the intermediate state and the final state, and because of electron-electron interactions in the final state, you may get additional discrete states in the final state that are not that you do not see in the intermediate state. Let's try to translate this into a Rix plane. So this is in principle Rix. Curved is nothing but Rix. It's the same thing. So if you excite into this discrete absorption, then this discrete state may decay into two final states that are shown here. Your next resonance, let's assume in this theoretical spectrum, or in this model spectrum, decays into this final state, and then then you get another dot here at higher incident energy and higher energy transfer in the Rix plane. And then you have the continuum excitations that occur as a diagonal line. Now you add your lifetime broadenings, and your Rix plane, your model Rix plane looks like this. You get the lifetime broadening of the intermediate state in this direction, the lifetime broadening of the final state in this direction. If you now take this high resolution scan, you move through a Rix plane like this. I hope you can see this little animation there on in the Zoom presentation. Yeah, so and then you see right away the sharpening effect, and you see additional features here, which is in this case actually not an absorption feature, it's a final state feature, so it should not come out in your calculations for an absorption spectrum. So it's a tricky scan that you take there, but it contains a lot of information. It's a useful thing. Let me skip over this. What is the problem there in an experimental problem that we face many times at the beamline is at what emission energy do you take your scan? I show here the Rix that's from a publication by Frank de Groot. I show the pre-etches in iron. So this is the 1s2p Rix, so the K alpha lines in this direction, absorption in this direction. So you have to decide now at what energy, emission energy, if you decide only to take Hertz scans and not a two-dimensional Rix plane, you have to decide at what energy you take your scan. There may be different philosophies, because you see already the spectrum will look different depending on where you draw your diagonal line there. Also, your emission scans, they have a chemical dependence, so they will move around when your sample changes, right? If you do a catalytic reaction, for example, the oxidation state changes, your emission lines, they will move around. So what is your experimental strategy? So either you decide that you try always to stay on the maximum of your emission line, which is not always obvious, because sometimes you do not know, if you have a chemical reaction, in which direction your line will move, right? In this case, you may choose to always keep your emission spectrometer at a fixed energy and just measure your spectrum at a fixed emission energy. You have to be careful, you never measure an absorption spectrum, and you can only do then, how can I say, a relative comparison of the spectra, how they develop with the chemical reaction. But you have to be aware that this is not an absorption spectrum, and this is nicely illustrated here. This is the Rix plane of serum dioxide sitting on the L alpha line. And now if you take diagonal cuts through your Rix plane at different emission energies, you get the red, green, and blue spectrum here. And you see that the spectral shape changes depending on your emission energy. Everything changes, right? Your pre-etch changes. Yeah, it moves around. You may think that you see an oxidation or reduction, but you don't. It's just a change of your emission energy. Yeah. So I'm just mentioning this. There is no good solution to this problem. You have to be careful. You have to be aware of this. And you have to decide on an experimental protocol. Obviously, one has to write in the publication what choice was made, and one has to be aware when then analyzing the data that one has this problem. Another thing I would like to quickly mention, Jerry, how much time do you have?
You're doing fine.
I'm doing fine. So the other thing, just a remark for valence to core emission spectroscopy. Would like to make some remarks. So that is, if you do this in the 3D transition metal, you excite your 1s electron into the continuum, and the valence to core lines are then from occupied molecular orbitals just below your Fermi energy. These are the valence to core emission lines. But how do you choose your excitation energy if you want to measure this at a synchrotron radiation source? One problem is are multiple electron excitations. Just to point out, you have the KH, obviously. If the energy of the incoming beam is high enough, not only to remove a 1s electron, but also a 2p electron, then with a certain probability this will happen. And this is the so-called KLH. The energy for the KLH is roughly the KH plus the LH energy of the Z+1 element. So if this is manganese, then manganese KH, then the KLH will be manganese KH plus iron LH. That will be the KLH for manganese, right? Because you removed already one electron there. They really exist, those KL beta lines. They will give rise then, yeah, to this. So this KLH will give rise to those additional fluorescence decay channels. And the probability or the intensity of those KL beta lines goes slowly up. It's called the Thomas model, slowly up over several keV. So what you would try in your experiment, you want to stay below the KLH in order, if you do valence to core emission spectroscopy, in order to avoid those multiple excitation lines, right? So you want to stay maybe a few hundred electron volts above the KH, but not too high. The other problem is if you look at very dilute samples, this is 1 millimolar of manganese. You want to look at your valence to core lines. If you now choose your incoming energy, which is the elastic peak here, if you choose it too close to the absorption edge, which is roughly 6,540 electron volts in manganese, you will have your fluorescence lines here sitting on the Compton edge, on the Compton background. Yeah, so you want to move your incoming energy away from your fluorescence lines as close to the KLH as possible. The KLH will be somewhere here. So you want to choose your incoming energy such that, as I said, that the Compton background is as small as possible, but staying below the KLH of your element that you're looking at. So I'm magnifying this area here. So all blue spectrum here is background that you don't want. It's the Compton line, it's the Raman lines as well. And this is the line that you're actually interested in. Yeah. So you have to wisely choose your incoming energy using those two parameters, the KLH and the Compton background. Another remark here, the fluorescence line is in principle isotropic in a polycrystalline sample or amorphous sample. The blue line is the A squared term of your interaction, so it has an angular dependence. It goes with the cosine square, the intensity or cosine square alpha of your scattering angle there. You try to avoid to go too far away from 90-degree scattering angle, otherwise your background will go up there. Yeah, so yeah, one has to choose the experimental parameters carefully there for the, if you look at the valence to core lines in very dilute systems. Yeah, so here, as I said, if you choose the crystals away from 90-degree scattering angle, you will increase your background. Okay. Maybe, Jerry, you tell me when I have a few minutes. There's a last thing, if you do HERFT high resolution XANES, there's a last thing that I would like to say. There's it's a fluorescence detected absorption spectroscopy, and fluorescence detected absorption spectroscopy always suffers of self-absorption or overabsorption, depending on how you want to call it. That is, of course, a problem, and many times you cannot avoid this. If you have an in situ cell, a catalyst, you will have overabsorption, and there's nothing you can do. I'm showing here an example of how you can possibly deal with this. There's no good solution. You can try to correct your data. That may or may not work. Many times you wonder whether the spectral changes you observe between different samples are due to overabsorption or a real chemical change. In this case, you could try to fit one spectrum or several spectrum on the other spectrum, do just a linear fit, but include overabsorption, right? So and this is the formula for overabsorption, and written in a little different form, and you can use in order you don't correct your spectrum, in fact you distort the spectrum that is less affected by overabsorption. You distort it deliberately on person by putting the cross section here into the formula, but that helps you determine whether the differences, the spectral differences, arise, as I said, from chemical changes in the sample or from overabsorption in the sample. So I give you an example here. So this is, I forgot, no, it's written here. So this is zinc in gallium oxide, and what was done here in this study, in this publication, the percentage of zinc was changed in the gallium oxide. So consequently, the overabsorption effect changes depending on how much zinc you put into the gallium oxide. And in this case, we try to, for the various samples, we try to find out how much zinc oxide is formed and how much zinc gallium oxide is formed. If you try to do a linear fit without including overabsorption, you get a bad fit of the sample there. If you if you include overabsorption, so you kind of compress your spectra using the formula for overabsorption, you do get a better fit. It's still not ideal, but it helps it just helps in the analysis, as I said, to analyze a little bit whether your spectra are affected, as I said, by overabsorption or by real chemical changes. Right here, you want to identify whether it's zinc oxide or zinc in the gallium oxide. And I see it's a 2:15. Jerry, I think I stop here and skip over my last thing, and I thank everybody for the attention. Are there more questions?
Yeah, wonderful talk. Thank you, Peter. I'll start with a question as people gather their thoughts. So the KL emission in the valence to core, it's relatively weak. I understand that it makes background subtraction a little bit more difficult, but why do you think it impacts the science enough that you want to prescribe this very specific energy for the incident beam?
I mean, there are many studies out there where the incoming energy was chosen above the KLH, and you get those KL beta lines at higher energies, so energies higher than the K beta.
Sorry, a little bit louder, Peter.
You get the KL beta lines at higher energies higher than the K beta 2.5 line. You could say you could deal with it, right? It's just an additional complication. If you don't have it, it's just easier, the analysis. I'm not saying that it's imperative. You absolutely have to stay below.
Yeah, I mean,
it just makes the analysis easier.
Yeah, I mean, the problem with the Compton, of course, is much less severe if you drag the Compton spectrum to higher energy. Okay, all right, thanks. Let's see, Matt Newell, do you want to ask a question?
Yeah, actually, I have two questions, Peter. First, I think it was the same question. Do you have a sense for the relative probabilities for the KL lines and the valence to core transitions themselves?
Well, you see it here, right? These are the KL beta lines. This is for manganese oxide.
Is that typical? Are those typical relative ratios or probabilities? Or is it just for that one? Because I know that the multi-electron excitations kind of vary widely in different systems. So
yeah, you have to. We just looked at the manganese oxide so far. It's something I always wanted to study a little bit more. But also be careful that the probability for those KL emission lines, or for increases over several keV very slowly. Look at the scale: 7,000, 8,000, 9,000, right? So it increases slowly over. So they do become stronger the higher you go. What really depends on the relative intensity between the KL beta and the K beta 2.5 here. To tell the truth, I don't know. As I told Jerry, you may be able to deal with it, and it's just something one should be aware of. It's not imperative. I didn't want to come across like you absolutely have to stay below the KLH. Okay. Just be aware and possibly.
I have a second question going back to your earlier portion of your talk. You talked about using area detectors to remove some of the dispersion from the Johan crystals. We see that too, as we're starting to do some Herfke, and I'm wondering if you have done any of those corrections, and because we see that effect, but we haven't made the corrections yet, and I'm wondering if you have, and if you have any advice on how to do that well.
No, we started doing the dispersion correction for this multi-wire detector that works, and as you know that on Simo Huotari, he proposed this dispersion correction for the diced crystals combined, and that works very nicely. It's used at the APS and the ESRF and probably in other places as well. So that works very nicely. And for us, no, we haven't done it yet. So I hope people will try more and more. And I think it's really driven by the new 2D detectors that we have that allow fast frame rates. And I think it's a new playground for all of us to explore a little bit what can be done there.
Okay, yeah, we'll try that too. We'll try that out.
Just a quick comment is we've done a lot of valence to core very non-resonantly with the lab spectrometer, and which is very high energy photons. And so the double excitations are a bit bigger maybe than what Peter showed, but they never get large compared to the K beta 2.5 or even nearly as big as the beta 2.5. That's the 3D transition metals. Later elements can be very different, of course. Neil, you have a question?
Thanks, Jerry. Thank you, Peter, for the very nice overview. My question is it possible to perform these hefty measurements in microfocus mode at in the tender X-ray regime or the hard X-ray regime?
I can only I'm not sure what is existing at the other synchrotrons, right? So please forgive me if I'm forgetting beamlines in the world where this is possible. At the ESRF, it is possible on it has been possible already in the past before the ESRF shut down for the upgrade on BM23. There is an instrument like the one that I showed you, like the hard X-ray spectrometer on ID26. A copy was built for BM23, and BM23 is working with a focus of roughly 3 microns. So this was done. There's a publication actually out by Alain Monceau, and the ESRF is building a new beamline, ID24. There will be a branch of ID24 where exactly the same spectrometer will be combined with a submicron or around 1 micron beam. Maybe elsewhere. Is that the beam size you were looking for?
Yeah, that's exactly right. I'll look that up. That's very helpful. Thank you so much.
In the tender X-ray range for ID26, we have roughly 30 microns, or will have with the new ring roughly 30 microns, 40 microns in the tender X-ray spectrometer.
Excellent. Thank you so much.
All right, another question, is the use of other crystals with better despacings for the tender X-ray range in principle possible with current technology for point-to-point geometries?
Yes, and I didn't mention this. I know that at SHRL, there is a publication, I think, out there. They use lithium niobate.
Yeah.
For, Jerry knows this, right? For sulfur, and it is very nice. Obviously, if you can work at a better Bragg angle, so a higher Bragg angle, everything gets much better. You get more counts, better resolution. Yes, there's always a quest for different materials. Yeah, it's an ongoing project. We're lacking resources there a little bit. I think all of us, we are struggling to get the crystals that we would love to have from the different providers around the world.